All right. So last lecture, you remember we were discussing basically models that we use for that we are going to use in the class, right? We discussed ordinary differential equations, and we saw how we can convert them to what we call a state space representation, basically system of first order linear differential equations, right? Today, I'm going to show you one of the fundamental ideas that are sort of behind all our effort in control theory, namely stability, right? If previously we saw a little bit what we are going to control, today we are going to see for what reason we are going to control something, right? So stability. Okay. If I can also control my my presentation. Okay. So okay. First, before we discuss stability, let us just discuss a little bit the solutions for differential equations. Those two things are going to be completely related. Okay. So if you have a differential equation of this type, x dot equals to f of x. So a nonlinear differential equation. It should be ordinary differential equation, but it doesn't have to be linear, right? And you have such x0 that f of x0 is equal to 0, right? Then this is called a node. So let us try to understand this just a little bit more carefully. So what does it mean for x0 to be such that f of x0 is equal to 0? Well, it means that it is such x that x dot is equal to 0, which in turn means that it is such an x which, if you landed there, your equation is not going anywhere. It's going to stay there. All right. Of course, there is an assumption that about t here, like we did not say pair of x0 and t0, for example, right? So if there is a time function that actually is going to take us out of this node eventually, that is a separate question. But for now, let us just assume that we don't care about pure time functions. We care about the x0. So x0 is a node as long as if we landed there, we're going to stay there, right? F of x0 t is equal to 0. That is the idea. That's the idea. So x0 will be called a node or a critical point. Okay. Okay. Now, we can call a node stable, right? If, and this is a standard definition of stability from Lyapunov theory, something called Lyapunov theory. We can call a node stable if and only if for any constant delta, there exists another constant epsilon such that x in the beginning, so x of 0, minus x sub 0, right? So initial x minus x sub 0 being distance away delta from each other implies that for any x forward in time, the distance between this x forward in time and x0 would be less than epsilon. Okay. So this inequality, that initial conditions are only delta away from x0 imply that any point on the trajectory of the system would be at most epsilon away from x0. That is what called stability. Right? But let us be careful. We're saying that there exists epsilon, right? We don't say epsilon is equal to something, right? So epsilon can be very large. Like we're not saying that because the initial conditions are only in this small distance away from x0, let's say delta is small, that implies that epsilon have to be small. Epsilon can be much bigger, but it cannot be infinite. Okay. So we can say that solutions starting from delta-sized ball do not diverge. So if our initial condition is delta away from x0, then we do not diverge. We do not go into infinity from there. Right? Now, this is the stability of a node, right? That's stability of a node. Okay, good. Before we go to more definitions of stability, and we would have, a couple more definitions, let me explain why we care about this kind of stuff. So when we are going to do control, what we will care about a whole lot will be how to analyze our performance in such a way that corresponds to real life goals, right? So imagine you're going to control a robot, maybe a flying robot, maybe a robot arm, maybe autonomous car. You want to understand what you can achieve. And you can imagine that maybe for a drone, you want to achieve like a velocity of certain amount, right? For a car, you want to achieve going through traffic this fast and so on. But first and foremost, before you can achieve anything else, what you want is for your system to not break, right? That is the first thing you want to achieve. And if your system is modeled by differential equations, then the solution to those differential equations going to infinity clearly indicates a break, right? Imagine we are talking about a car. The solution of differential equation that describes your car goes to infinity. What does it mean practically? Well, your variables have something to do with physical values that describe the car. Let's say velocity is other. If a solution goes to infinity, it may well indicate that your energy goes to infinity, right? Unless we're talking about infinity as in like your position goes forward, you're just driving and driving. That's fine. But if your velocities go to infinity, that means your car gains energy, and sooner or later something will break. What will likely break is your model. Like there will be disconnect between how you model your car and what actual car does. Actual car will just run at the top of its abilities. Your control system will assume that it runs at much higher rate. There will be disconnect, and eventually, nothing good will happen. Something will crash, right? If you do control of a robot arm, you can imagine what a instability looks like. Let's say the robot arm tries to, go from point A to point B, but the initial small error at point A leads to exponential increase, or just like unbounded increase in the error at the point B. So instead of going to point B, it goes somewhere and just crashes into limitations, like in the box that surrounds your assembly line. You can see that in some sense, all of this is just a discussion of absolutely worst case things that can happen. Instability means that you lost control over your system. Your system does terrible things, right? And that is what we want to avoid. Stability, on the other hand, so this implication that you have bounded initial conditions lead to bounded trajectory, it means that you can have some expectations of what your system is going to do. Like, let's say you started your pick and place from a certain position. You will end up in the next position, maybe with an error, right? You didn't pick here, you pick here. All right, error, not good. But at least you have some expectations that it will be somewhere close to where you're going to pick, right? If you're doing airplane control design, you can say that stability at least make sure that our small variation in the orientation of airplane is not going to lead to unlimited change in orientation of the airplane. If your airplane does unlimited change of orientation, it's going to do something that you don't want to see, right? So stability somehow is a question of preventing things that you definitely don't want to have, right? But in itself, it might be slightly insufficient. So let me introduce another notion which would make it much more attractive, I think. 1 second. Now, here is a notion of asymptotic stability, right? Asymptotic stability. It goes like this. The system is a system or a node, in this case, right? Node is asymptotically stable if for any constant delta, it is true that initial conditions being delta distance away from x0 implies that as time goes to infinity, the solution will approach x0. All right? So the solution starting from delta-sized ball converge to the node. All right? That is asymptotic stability. So big difference between those two is that here, what we have is like we don't diverge, right? We start from delta-sized ball, we end up somewhere epsilon away from the node, right? Here, on the other hand, we start from delta-sized ball, we end exactly at the solution. So we approach the asymptotically. Now you can see this is much more attractive. Remember our pick and place example. I pick here with an error, right? I want to place here, but if enough time passed, I know I will place exactly where I'm supposed to place, right? Here I'm simplifying it a little bit because, here we're discussing, of course, the same node, right? Here and here, right? So please forgive me the liberty of examples. But better example, okay? Airplane starts with a small tilt in its orientation. As time goes forward, the tilt will have to decrease because eventually we'll have to have zero divergence from the node. So if the node represents normal orientation of the airplane, then as time goes to infinity, our solution has to approach it. Instantly very attractive. Instantly very attractive as a solution. Right, so those two are our working definitions. Do we have any questions about them? No? All right. Yeah, just as a reminder, please don't hesitate to ask a question during when I talk, when I pause anytime, right? I will be happy to answer. Okay, let's go on. So some examples of asymptotic and regular stability. So let's just look at this dynamical system. X dot equals to 0. That is a differential equation. That's a first order ordinary differential equation. So it corresponds to how we described our system in this chapter. So let's consider solution x equal to 7. Oh, there is a chat. What's the purpose of that? Right, Marat, I'll finish this example. I'll answer your question, okay? Good. Thank you for the question. Just one moment and I will get to it. All right, so we'll consider this dynamical system, x dot equals to 0, solution x equal to 7. So this is indeed a solution. How do I know that the x equal to 7 is a solution? Well, I differentiate it. 7 differentiated gives me 0. So 0 equals to 0, equation becomes equality. So this is a solution. Solution is stable, but not asymptotically stable. How do I know? Well, let's say initial condition is equal to 7 plus delta, right? Well, any solution forward in time would also be equal to 7 plus delta, because solutions for this equation do not change, right? X dot is equal to 0. So what you start with, you stay on. So they don't diverge, but they don't converge to x equal to 7 either. So x equals to 7 is a node, but it is not an asymptotically stable node. It is just stable, right? Another example. Dynamical system x dot equals to minus x. And solution x equal to 0. Well, is this a solution? Well, we put 0 here. Derivative of x is also 0. So we have 0 here. Indeed, it is a solution. Is this a node? Well, we put 0 here. X dot is equal to 0. Yeah, indeed, it is a node. Right? Okay. So this solution is stable and it is asymptotically stable. Why? Well, if we start from any other solution, any other initial condition, delta v. So let's say we start with a solution x equals to, let's say, 3, right? What's going to happen to this equation? How is it going to evolve? Can someone tell me the solution to this differential equation? X dot equals to minus x. How is the solution of this equation looks like? Please just unmute and talk. I'm sure someone knows, right? Should we solve it? Do you want me to solve it? It's not difficult. Do you want me to solve it on the screen?
Yeah.
All right, good. So how do we solve those equations? Well, we say dx dt is equal to minus x. I'm going to just do the do the solving using standard, standard approach. So we do that, right? Then we, as a next step, we say dx divided by x is equal to minus dt, right? So what I did here is I split this dx dt into two differentials, right? Multiplied both sides by delta t, right? dt, and divide both sides by x. All right, good. Now, as a next step, I integrate both sides, and we get on the left-hand side logarithm of x. On the right side, we get let me just be careful, okay, minus t, but there is a small detail that I'm missing. constant of integration, right? Constant of integration. So if you allow me, I will just write it like this. But I know this is a rough derivation. So if you want, how should I put it? You should be careful about like each of those steps. So if you're going to look into it more carefully, I would encourage you to consider each of those steps more carefully. Like how do you justify the constant of differentiation appearing here, etc., etc. Right. As a next step, I take exponentiation of exponent of the both sides. So I get x equals to x of minus t plus c. And next, we recognize that this is the same as this, right? I would just prefer a constant to be on this side, right? And that is the answer, more or less. We can also find out what this constant is. Like exponent of a constant is still a constant, just a different one. So we call it C0, right? C0. Now, what is C0 equal to? What is C0 equal to? Well, we know that x equal to 0 is a solution, right? So if we put, will it help us? Let me just think. Let me just think. Oh, no. X equal to 3 as initial condition. Let's put x, we'll do it this way. We'll say x of 3 is equal to 0, right? Therefore, we put 0 here, put 3 here, and this implies that the constant C0 is equal to what? Oh, here, 0, right? Exponent of 0 is 1, right? E to the power 0 is 1. So 3 equals to C0, so C0 is equal to 3. And with that, what we have is final solution to the equation. The solution to the equation is x equal to 3 times exponent of minus t. So is this a familiar process for any of you?
Yep, we know it.
Okay, good. Good. So this is a solution to this equation. And if you assume look into how it's going to behave, I think you would agree that this guy is going to decay to 0 as time goes to infinity, because exponent of a negative number is going to is less. How should I put it? How should I put it simply? Like exponent of -1 is 1 over e, right? Exponent of -10 is 1 over e to the power 10. So it's much smaller. As time goes to infinity, it's going to become close and close to 0. So this solution is going to exponentially approach 0. And as we see from this step and this step, right? No matter what initial conditions we pick, it will only influence this this multiplier. It will only influence this constant. The solution itself is going to decay to 0 regardless of initial conditions. That clear?
Yes, it's clear.
Okay, good. All right. Now, one more example. Let's consider dynamical system x dot equals to x and solution x equal to 0. So this solution is unstable. I would just write down solution here. It is would be the same process, but the solution here would be x of t equals to t initial conditions, right? Times exponent of t, right? Exponent of t. So the minus sign that was here is not here, so exponent would be positive. So as time goes to infinity, the solution would exponentially increase. So any c which is not 0 will lead to a solution that goes away from the node x equal to 0. Right, so that is 3 examples. Now, let me quickly answer the question about what is the purpose of delta in the stability definitions. Let's look at this example. So the purpose of delta is simply to define what we mean by stability. Stability does not is not a property of one point on the phase space. So like it's not a property of x0 alone. It is a property of x0 and the neighboring solutions. All right. So there is a solution starting from x0, and then there are solutions that start from points close by. Stability is a property of all of them together, right? Not only x0, but the solutions that are close by. That is the whole point. Because the solution that starts from x0, in our case, we're considering a node, so it is trivial, right? It's just nothing happens. So, the system sits there. We do not have to do it this way, by the way. Stability would have worked perfectly well if we defined distances from initial conditions of two solutions and distances along the trajectory. It would be exactly the same. But for us, nodes are enough, right? So delta is just to mention that we consider solutions around us. We could realistically get rid of delta for some cases. From the definition, right? We could get rid of delta from the definition, but you have to ask yourself, what would allow us to do it? And what would allow us to do it to get rid of delta is some kind of class of systems where all solutions behave sort of similar, right? So if a node is stable, it is stable for delta which is as large as you want, right? Where it doesn't matter really like what delta you pick. There would always be how should I put it? If there would be no question of like local properties. If you can perfectly well work directly with global properties, then you can maybe realistically get rid of delta from this definition. Let us move forward with lecture, and we'll see if maybe there will be something like that in there. By the way, before I move on, any questions? Any more questions? No? All right. So now let us consider, go back to what we left with in our last class, namely systems of this form. X dot equals to AX plus BU. Let me quickly remind you the terminology. So that is state space form. X is called state. That is a state derivative, right? That is a state matrix. That is control matrix. That is control, right? We call the system linear time invariant. That is just a useful thing to know. Linear time invariant. Why we call it this way? Well, because A and B are constant. So they don't change with time, right? You remember in our definition earlier, here, there was this T, right? At the very least, in these examples here, we know that A and B themselves do not depend on T, right? Now, U may depend on T, but A and B don't. That is what it means to be linear time invariant. Now, if we remove U, we would get a simple equation. This simple equation is called autonomous system. Why autonomous? Well, it is autonomous because its evolution forward depends only on the state of the system. So it does not depend on time at all. So in our original equation, where there was T, we could remove it altogether, and we would have perfectly valid description of the system. It depends only on the state. If we know initial state, we know the whole trajectory of the system. So two trajectories, if they're distinct, would never cross each other, because if they crossed, they would share a single state. If they share a single state between them, it means that they would have to follow the same path forward, right? That is quite interesting. Autonomous systems, they depend only on the state. Oh. Basically, what I want you to get for now from this is, we call it autonomous, and they those systems, and they have interesting properties. For us, the goal will be to analyze them in terms of stability. Right? Okay, let's move forward. So let us consider the following autonomous LTI, right? So autonomous linear time invariant system. X dot equals to D of X, where D times X, where D is a diagonal matrix, all right? So D would be here a diagonal matrix with coefficients D1, D2, Dn on the diagonal, right? So this equation would then be equivalent to a system of independent equations. It would be equivalent to x1 dot equals to d1 x1, x2 dot equals to d2 x2, all the way to xn dot equals to dn xn. That transition is clear from 7 to 8? Or do you want me to illustrate it a little bit more? Please ask me to, clarify, when something's unclear. Otherwise, I would feel compelled to clarify even if it is clear. So,
it's fine. Thank you.
Fine, right? Right. Just in case, I would quickly show what I mean, right? Like diagonal matrix means that we have elements like this, right? So we have, x1 times this element gives us equation here. Right? x2 times this element gives us equation for the here. Right? x3 times this element gives us equation here, and so on, right? So like x1 is only multiplies this element. It does not include itself in any other equation. x2 multiplies this element, it doesn't include any other equation. When you multiply them, you get x1 equals to d1 x1. x2 dot equals to d2 x2, and so on. Okay. So equation 8 is the same as equation 7, just written as system of independent equations. Now, each of those equations, we already solved this kind of stuff, right? So each of those equations has a solution. xi equals to ci e to the power dt, right? dit. I think it is clear, like the way we solve it is the same as in the previous example, right? So I'm not going to repeat it. It is just that there was this coefficient in front of t. For us, in our example, it was -1. Here it is this guy. Can be any number. It would still be in front of t. And it would determine how the solution will behave. If d is a negative number, we will clearly converge to 0, right? Not to just like any solution, specifically to 0, right? We'll converge to 0. If d is positive number, we will diverge to infinity. Now, if d is equal to 0, the solution will stay in place. So the solution will be just xi equals to ci. So 3 possibilities. Less than 0, we converge to, if d is less than 0, we converge to origin, to 0. Right? If d is more than 0, we diverge to infinity. If d is equal to 0, we stay in place. Right? So 3 possibilities. Now, both negative d or d that is equal to 0 give us a stable equation. The node to which we converge is always 0 solution, right? You can imagine this equation, equation 7, has 0 as a solution, right? So 0 is a solution to this equation. It can have more solutions if one of the d on the diagonal is 0. Then we can have more than one solution. But if it is full rank, if d does not have any 0 coefficients on the diagonal, then the only solution is 0 solution. All right. If it is unclear, you can think about it. I'll probably include this a little bit more in the following lectures. But if you want, you can just think about it for yourself. Is it true that for full rank D or any other full rank matrix, the only solution to this type of equation is 0 solution? Right? Now, this basically gives us a discussion of stability. Let me just double check. All right. So this gives us a discussion of stability. So this equation and its 0 solution, so x equal to 0 is a solution, is stable if and only if all d, all the coefficients on the diagonal, are either negative or 0. And it is asymptotically stable if they are all strictly negative, right? So that is the difference between stability and instability here. It will be unstable if there is at least one positive coefficient. Any questions about this case?
Can you please repeat one more time what's the difference between not diverge and converge?
All right, so let me, I guess, like just introduce one term. We're going to use it anyway, so I can introduce it now. So we have something that is called marginal stability, all right? Marginal stability. So this definition is essentially this definition is a definition for what we call marginal stability. I just call it stability here because that is also true. That's how we also call it. But we call it marginal stability. What does it mean to be marginally stable? Well, it means not diverge, right? If you not diverge, that means you are marginally stable. The word marginal here just means like barely, right? Like a small change will make you unstable. But in the system, right? But yeah, marginally stable. So it means you do not diverge. Now, this guy is asymptotically stable. It means that you converge, right? So marginally stable, you do not diverge. Like you can converge, or you can just stay still, or you can, do something but not blow up. That is marginal stability. Right? Asymptotic stability means you converge. You converge to the solution. Make sense?
Yep.
Okay. Now, in this example, if D is positive, at least one of them, you diverge. So you're unstable. If D's are non-negative, non-positive, so negative or zero, non-positive, then you are at least marginally stable. If at least one of them is zero, you're only marginally stable, right? But if all of them are negative, then you are asymptotically stable. So asymptotic stability is a more demanding definition than marginal stability. Marginal stability can be achieved even if you have zero in your diagonal matrix here. All right. But asymptotic stability requires strict negativity. Make sense?
Yes, thanks.
Oh, thank you. Good question. Right. By the way, those D, D1, D2, D3, etc. on the diagram, they are eigenvalues of this matrix, just so you know. That's kind of obvious. Elements of the diagonal matrix are its own eigenvalues, but just so you know, they are eigenvalues of the matrix. So the criteria here is that eigenvalues should be negative for asymptotic stability, non-positive for marginal stability, and if at least one of them is positive, it is unstable. Okay, all right. Now let us consider a much more general case. X dot equals to AX, so still autonomous LTI. We discuss stability for autonomous LTI again. But now we only assume that A has eigendecomposition of this form, where D is a diagonal matrix. So let me be careful what this means. So A has real eigenvalues. So all eigenvalues of A are real numbers, which allows us to find eigenbases V and eigenvalues that are put on the diagonal of the matrix D. And this gives us decomposition A equals to V times D times V inverse. Well, that is a standard decomposition. If you think, where did this come from? Is this new mathematics? But you remember eigenvalues, then consider that this is the same as writing AV equals to VD, right? That is the same exact thing. I just multiplied on both sides by V, right? And this already sort of should look to you like a definition of what it means to be an eigenvalue, right? Your definition is usually only presenting one eigenvalue at a time. So you would usually have only one vector V here, and instead of the whole matrix of eigenvalues, you have only one single eigenvalue. But if you think about it, this is just like stack of those equations put together. So this decomposition, the fact that it exists, it's not strange mathematics. It is a consequence of how you define eigenvalues. Whether all of you have a clear memory of eigenvalues, right? It's like we don't need a refresher on eigenvalues, right?
Right.
Right. Okay. The eigenvalues is a strong, prerequisite for the rest of the lecture. Okay. We have this decomposition, which allows us to replace A matrix here with V times D times V inverse here. Okay. So X dot equals to V times D times V inverse. It is a replacement for A matrix. Now we can do a trick, we multiply both sides by V inverse. So we would have V inverse here, V inverse here, right? Here's the result. Okay. We multiply by V inverse on both sides. And we notice that V inverse times V is identity. So this part goes away. Now, second trick, we introduce new variable, Z. Z is equal to V inverse X, right? Okay. So now this guy is Z dot. This guy is Z. With that, the whole equation becomes Z dot equals to D times Z. You see what I did, right? First, I multiply on both sides by V inverse, and I got rid of this guy. Then I introduced new variable, and instead of having something like this here, I just got a new variable on the right-hand side. And on the left-hand side, of course, right? So we have a new system of equations. Z dot equals to dz. What is interesting is since D has real elements, so it's a diagonal matrix, it is the same as the previous example. So we already know how to proceed from there. So we know that in this case, the system will be stable if elements of D are all non-positive, so negative or zero. It will be marginally stable if there are zeros on the diagonal. It will be asymptotically stable if all elements of D are strictly negative. But elements of D are again eigenvalues of the matrix A. So let me repeat what I said previously. This equation will be stable if asymptotically stable, right? Asymptotically stable if all eigenvalues are strictly negative. It will be marginally stable if they are non-positive. If at least one of them is positive, it is unstable. And notice that like we have this like chain of results, right? Like this result depends on this result, right? And this result depends on what we did with this example, right? So it becomes more complicated, but each time we go back to what we previously have seen. Do we have questions about this proof? Or anything else? Okay. Now, we will take a small sort of like pause from making more and more general statements. For now, let me just give you a observation about a specific type of matrices, right? It would be useful for you, especially since like this type of matrices, it is very easy to put them on exam papers and like other tests. So, maybe if you want to, you can listen. It's those matrices are special case, but they're also good for understanding. I think they help you understand a little bit better stability. All right, so upper triangular matrices. What do we have here? Well, upper triangle matrices look like this. You have elements of the diagonal and on top of that, right? So that's why we call them triangular, because they form this triangle, right? So elements on the diagonal and on top of that. Nothing below the diagonal. Okay. Here's the rule. Eigenvalues of upper triangular matrices as the diagonal elements of those matrices. That is a key rule. So eigenvalue of this matrix is 1, 3, and -2. Eigenvalue of this matrix is -2, -2, repeated eigenvalue, right? 7. Eigenvalue of this matrix is 4 and 3. So they're all real numbers. Eigenvalues of those matrices are all real numbers, and they are right there, like on the diagonal. Okay. Now, for upper triangular matrices, we can prove that stability depends on the eigenvalues without eigendecomposition. It is much more straightforward to prove that it is depends on diagonal elements of the matrix. Let me show how the proof goes. So let's consider this system with upper triangular matrix M. So let's assume that the eigenvalues, so elements on the diagonal, are negative, right? We call them N11, N22, M, and N, right? So elements of the diagonal numbered like that. So let's consider the last equation in this system, which goes like this. X dot sub n equals to M sub n, so the last element of the diagonal, times xn, right? So the last equation is like this, right? Now, since M sub n is negative, we can solve this equation, and we know the solution. Solution is xn of t is equal to, constant times exponent of m and n times t. This is a negative number. So this variable xn will go to 0 as time goes to infinity, right? It has to go to 0 because this equation, its solution goes to 0, right? Because m and n is negative. Okay. Now let's consider previous equation. So the equation before the last. It would go like this. X sub n minus 1 is equal to m sub n minus 1 times x sub n minus 1, right? Plus x sub m minus 1n times xn, right? You understand that you have this matrix. It's I'll draw it like this, right? Since it is upper triangular, you would have elements here, element here like this, right? Element here like this, and so on. When we considered the last equation, there was only one element there. It depended only on xn. For the equation before last, we have two elements, this one and this one. So this one and this one, all right? But this equation depends on xn, and xn goes towards 0 as time goes to infinity. So as time goes to infinity, you can ignore this contribution because it's going to go to 0 anyway, like this part. So we only need to consider this part of the equation. And this part of the equation has the same structure as this one, right? It also is, variable times a negative constant. Derivative of variable equals to negative constant times the variable itself. So it has the same solution, exponent with a negative number in the exponent. So it also goes to 0, right? And we can repeat it for all equations. For all equations, everything that comes from those contributions which are up above the diagonal will have already been proven to decay to 0 because of the previous equation, previous equation always proves that everything that you add to the next one is decaying to 0. So we would only have to consider diagonal contribution, and diagonal contribution would decay to 0 itself because of negativity of the diagonal values. So this argument does not require eigendecomposition. It's just a question of considering each equation and noting that each equation proves that one of the variables decays to 0, helping you to prove next equation. Right? Okay. If this is clear, great. If not clear, you can meditate over it after the class. It is nice, I think, to think about. It gives you an intuition how to think about stability, right? How to think about stability. So thus, we can see one more time that for this equation, negative eigenvalues imply asymptotic stability. Right? I did not try to prove here instability with positive eigenvalues, but you can clearly do it by yourself. Right? It would be more challenging here to prove marginal stability, right? If one of the elements is actually 0. But I invite you to do it if you want. You can try. It it is possible, and it will be interesting. Any questions about this? All right. Before I move on, we still have a little bit of material. I mean, like quite a bit of material to cover. So can you please tell me how much time we have? Can someone tell me?
We have 30 minutes.
30 minutes. All right. Hopefully we'll make it. All right. Good. Now we will consider a more complicated case, right? More complex case. We have a system, 2x2 system, right? With complex eigenvalues. Here is a system, x1 dot x2 dot equals to this matrix, alpha minus beta, beta alpha, times x1, x2. So this system has eigenvalues alpha plus or minus I beta. Right. For notational purposes, we denote x1, x2 as x bold. Right. So let us consider stability of the system. Here I'll make an interesting argument of how to analyze stability of the system. The argument is slightly different from what we saw before, but hopefully it will be clear. Let's see if we can manage. So first I make a claim. I claim that for the system to be stable, so let's say asymptotically stable, x dot times x should be negative. We're talking about the dot product here, right? So dot product of x dot and x should be negative. Let me try to justify this claim, right? So I made a claim. Now I need to justify it. First, any vector, x dot is a vector, can be decomposed into sum of two orthogonal components, right? So in this case, I will decompose it into a sum of x dot parallel, which is parallel to x, and x dot perpendicular, which is perpendicular to x, right? So visually, if you imagine this is your x dot, and maybe if, let's say, this is your x, like x dot, and that is x, right? What I do here is a decomposition that looks like this. Let me, I guess, just one second, let me try to see if I can rotate it a little bit more, maybe like this, just so the decomposition is more clear. So how would the decomposition look like? Well, I describe it as this component which is parallel to X, right? That's one component. And this component which is perpendicular to X. So those are two components into which I decompose my dx vector. That is all. Just I represent one vector as a sum of two. Okay, all right. Now, by definition, this perpendicular component, when it is multiplied by X via dot product, it is going to be equal to 0, right? So perpendicular component times X is going to be equal to 0, right? So in terms of this product will be equal to the product of X parallel times X. X perpendicular does not influence this product at all. In fact, X perpendicular, if we are considering what's going to happen with X as a result of X perpendicular, if we integrate it forward, it's going to rotate X. It's not going to change its length, right? X dot is the rate of change of X, right? So component which is perpendicular to X is going to change its orientation. It's not going to change its length instantaneously. We're talking about instantaneous change. All right. What about X parallel? Well, X parallel is exactly what is responsible to the change of length of X, right? If X parallel is, you can see it on this picture, right? This component is X parallel, right? If it looks into the opposite direction of X, as you integrate it, X will shrink. If they look in the same direction, X will grow, right? If this is somehow unclear, I think you should have a little bit of numerical methods or something, but you can imagine that you can approximate integration of X dot as something like this. X of, t plus delta t is approximately equal to X of t plus dx dt. Right? Something like this. It is like a very primitive approximation of integration. Right? Now you can imagine if dx here is this perpendicular component, what's going to happen is X will change direction, right? You have this X vector, you add this component that faces this way, it will just rotate instantaneously. Again, we're talking about instantaneous change, not over like big periods of time. If I have this parallel component here, it's going to either shrink or increase. Well, if dx looks into the same direction as X, if they are collinear, then X will increase in magnitude. If they look into the opposite direction, X will shrink in magnitude. So that is how I justify this claim. What you need to know is just if X dot times X is negative. That is all you need to know about this equation. If they're negative, it is asymptotically stable. We can also try to make a claim that if this is equal to 0, it's marginally stable, but for now, I'm happy enough with just a statement about asymptotic stability. All right? If there's any question, please, please ask. Okay. Now, using this result, let us compute what this product actually is. Well, the way we compute it is we just multiply this matrix by this vector. What we get is alpha times x minus beta times x2, like alpha times x1, beta times x2. We get beta times x1 plus alpha times x2. Next, we multiply this guy by this. We get alpha x1 squared minus beta x1 x2, right? Let me write it here. Alpha x1 squared minus beta x1 x2, right? That's what we are going to have when we multiply those two together. Next, we multiply, let me use different, this guy by this guy. What do we get? We get x2 x1 beta plus alpha x2 squared. Now, notice that we already had this component, beta x1 x2, but it is negative here. Here, when we multiply, it was going to be positive. So they will cancel. They will cancel, right? When we add, x2 x1 beta plus alpha x2 squared to this expression, they will cancel. So what will be left is only this part. X dot times x equal to alpha times x1 squared plus x2 squared, right? This component plus this component. That's what's going to happen. Now, notice that this product is negative if alpha is negative, right? That's what we've proven. But alpha is a real part of the eigenvalue. So what we've proven is that as long as the real parts of the eigenvalues of the system are strictly negative, the system is asymptotically stable. Now, what we did not prove, but I would ask you to trust me or to try to prove by yourself, is that if the real parts of the eigenvalues of the system are 0, then it is marginally stable, right? Then it is marginally stable. Okay. All right. So this is the way we proven this property, but we proven it only for the system. That's a small omission, right? We've proven how stability criteria for systems with complex eigenvalues, but only for 2x2 system. Now let us generalize. Before we do, let me just show you this interesting picture. This is called a vector field. So each arrow here basically represents this x dot vector. Each coordinate represents x. So this is point, like this point here, is where x1 is equal to 1, x2 is equal to, x2 is equal to 1, x1 is equal to -1, right? Point in the center is 0, 0. That point is 1, 1. That point is 1, -1, and so on, right? Each arrow represents, again, the derivative. What does the graph represent? Oh, the graph represents the solution to the equation that starts from this point. If it started anywhere else, it would also have the exact same shape because, it doesn't matter on which point on the trajectory you start, you would follow it. What is nice about vector field graphs is that you can just by connecting the dots, draw the solution, kind of. Not really, but kind of you can. Like here you can see that solution is roughly speaking going to go like this, right? Roughly speaking, it's going to go like this. Right? It also helps when you draw new solutions to know that you cannot intersect previous solutions. That's also nice. If you intersect the previous solution, at the point of intersection, you have to ask which path you follow forward, and you cannot have two options. So that's why the solutions never intersect. All right, and you can see that this is how it looks. Now, this is how a solution to this case of complex eigenvalues look. All right, now let us generalize this finally to as general cases we are going to consider in this course. So consider system x dot equals to ax, where A have eigendecomposition, but with complex valued C matrix and complex valued invertible U matrix, right? So we have C matrix here, which is your, it's a diagonal matrix, but with complex values on the diagonal. And U is a eigenbasis, but also complex valued. We can do exactly the same as we did before. So replace A with U times C times U inverse. Multiply both sides by U inverse. We get one here, right? Then we introduce Z equals to U inverse X. Z is also going to be a complex valued vector, right? So this will become Z dot, this will become Z, right? Here, as before, the thing will cancel. So we would get this expression, Z dot equals to C times Z. So far, exactly the same as before, just the values are complex. This falls into system of independent equations, right? System of independent equations. But the equations are complex valued. So we have Z dot equals to C times Z. Those are complex equations that come from this diagonal matrix times vector. All right, good. Now let us expand those two values, C, again, this is a coefficient on the diagonal, and Z, that is our new variable. So C will be alpha plus I beta, Z would be U plus IV. I drop the subscription J just to avoid crowding the slide. All right. Now let us compute what this would be. Well, Z sub J, like when we substitute those values, it would be equal to U dot IV dot, right? That's Z dot, equal to alpha plus I beta times U plus IV. When we multiply all of these things here, we get alpha times U, a real value, I beta times IV minus, I times I gives you -1. So again, a real value. And we get two complex valued variables, I beta U, I beta U, and I alpha V. So I alpha V. Right? All right. But now we can arrange it in this shape. That's interesting. How did we do that? Well, we'll put real values here. So real values U dot on the left-hand side is equal to alpha times U minus beta times V, right? That's on the real values. Complex values next line, I V dot equal to beta times U plus alpha times V. And this is exact same as in the previous example. We already analyzed the system. So equation 22 is the exact equation we analyzed previously. And we know the solution. If those values C, I have real negative real parts, it is asymptotically stable. Marginally stable if they are 0. Unstable if they are positive. So we can see that complex parts do not influence stability. Asymptotic stability is not influenced by them. All right. That is as difficult as it gets in this lecture. We're not going to see any more crazy mathematics. Now, before I go on, let me just give you a definition, final definition for this lecture, stuff that we have been trying to work towards, and then a couple minutes of discussion. Right? So, if you have autonomous LTI, you can analyze its stability, right? You can know how it behaves. And analysis is very simple. If real parts of eigenvalues of A are non-positive, then it is marginally stable. Or we can just say stable. If real parts of eigenvalues of A are strictly negative, it is asymptotically stable. And this is true for any matrix A, all right? It can be have complex eigenvalues, can have real eigenvalues. This definition holds. I say definition, but it is essentially criteria. There are many ways to determine stability of a system. There's many ways to determine how it's going to behave. This is just a criteria. But it is very useful. So and for us in the computer age, where we can just calculate eigenvalues by typing like eig of A, right, in your favorite language, be it Python or MATLAB or whatever you're going to use. It is very easy to get eigenvalues of a matrix, much easier than almost any other criteria. So that is what we're going to use here. Any questions about this? Right, no questions. So now we understand what stability is, and we understand how to check for stability. We saw quite a few proofs of stability for simple systems. I did not give you a general proof, right? I did not give you a general proof. General proof requires a little bit of additional mathematics. So if you want to see general proof of this fact that they are present here at this slide, you have to check a textbook which would contain like a general proof for eigenvalues, right? There's just a little bit more mathematics at what I was presenting here, a few more facts from like linear algebra. However, for understanding, I think what I showed here is maybe good enough for the introductory course. So that is my motivation for giving you this lecture with like this types of proofs, right? These types of proofs. In fact, this type of argument is going to be directly useful for a whole lot of stuff that we do in control theory. Like this type of decompositions is just actually useful tools that we are using, right? And this, I think, is good for your intuition. But please remember that like even this argument, that is not a general argument. General argument requires Jordan forms. So like more general piece of mathematics. It has to do with the fact that we just assumed that there are all those decompositions, whereas something like repeated eigenvalues and so on, okay, I'm not going to go into it, is going to prevent us from having this assumption in general, right? But this fact is true. Like this criteria is correct. I just did not give you the most general proof. Okay. Now, I think we have still a little bit of time remaining, no?
10 minutes.
10 minutes, okay. Very quickly, I will show you illustration of how systems behave during, depending on their stability status. So, for example, Lyapunov stability Lyapunov stability is yet another name for marginal stability, all right? So we can call it stability, we can call it marginal stability, we can call it Lyapunov stability. So system with a Lyapunov stability can go around the origin in a circle or in elliptical orbit, something like this. So it can just go around, that is a normal behavior for Lyapunov stability. Doesn't have to be like that. It can just stay in place, but it can also go in orbits. Asymptotic stability implies that you eventually go towards the origin. Again, for linear systems, when we're talking about the fact, we're talking about linear systems where the only solution is the origin, all right? Only solution is the origin. Now, if the system is unstable, here is how it can behave. It can go towards the origin, but then it can sort of like sling out. Go towards the origin, sling out. Right. So here, this would be a direct eigendirection where eigenvalue is positive. This will be eigendirection in which eigenvalue is negative. All right. So that is instability. That's typical behaviors. Let me see if we have anything else. Now, those are like phase portraits. And here you can see by the direction of the arrows that the direction of this trajectory goes like this. And you can see that it actually is stable. It converges towards 0. That's how you can read the phase portrait using arrows. Here, you can see that the direction is like this. So it goes towards the origin. So this is asymptotically stable. Both of those are asymptotically stable. This guy here goes like this, and like this, and like this. So this is unstable. This here goes like this, and like this, and like this. So again, unstable. Well, those are two examples, some examples of stability and instability in phase portraits. Right. Now, in a few times, I how to put it? I mentioned like especially here, I mentioned that we decay to the origin, right? We go to the origin. Now, let me just give a suggestion of how to think about this. Consider this system, okay? Consider this system. Let's say that x0 is a node, right? We substitute, that implies that a times x0 is equal to 0, right? Because there's a node, so x dot at this point is equal to 0. Now, if A has strictly negative real parts of eigenvalues, okay, let's assume that it has real eigenvalues. So strictly negative real eigenvalues. Well, it means that, and let us go to the slide where we have example. It means that A would be represented as a full rank matrix times full rank matrix times full rank matrix, right? So A is a full rank itself, okay? Now, if A is full rank, what does it say about this equation? How many vectors can you multiply full rank matrix by to get a 0? Someone answer me. How many vectors can you find which you can multiply a full rank matrix by them to get a 0? That is a linear algebra. It's not differential equations. So, I'm sure you remember. No? Let me remind you. This equation implies that x0 is in the null space of A. For full rank matrix, null space is trivial. Trivial means that it contains only one vector, 0. So you can only multiply A by 0 vector to get 0. So that is the reason why we were so nonchalant about explaining which node we talk about. Like, notice in this proof, there is no mention about which node we are talking about. In this proof, there is no mention about which node we are talking about. Here, neither. Here, neither. Here, neither. Right? In fact, if system is asymptotically stable, it implies the matrix A is full rank. It implies that the only node that exists is the origin. This does not limit our ability to control other parts of the state space, but it sort of makes it unnecessary for us to discuss this whole thing about which x0 we mean. You know, if it's asymptotically stable, the x0 that we mean is actually x0 equal to 0. Yeah. And the discussion of delta, as you remember, there was a question in the beginning by Marat about delta, is if it is necessary or not. You can see we were able to dispense with it because we know simply that origin is our solution, and either every other solution converges to origin, or does not diverge to infinity, or it's, there are solutions that diverge to infinity. Those three definitions are there. And, this way we were able to dispense with this delta. But that is because we are considering here LTI, linear time invariant systems. And in fact, autonomous LTI, right? Autonomous LTI. That is how we were able to quickly get so many good results. We limit ourselves to a very small class of systems, but we get all this information about them still. All right, that is it for now. Next class, unless I'm mistaken, we are going to consider the question how to make a system stable, right? So far, we considered the question of if it is stable or not. So, what we're trying to understand what we actually should care about. Next time, we'll understand how to do things. Okay. Right, but that is it, I think, for the material of the class. Let me stop the recording, and if you have questions, I would like to answer.